In this video, we're going to look at the consequences of our basic definition of simple harmonic motion. So we've seen that a particle is executing linear simple harmonic motion if it's moving in a straight line in such a way that its acceleration is proportional to the distance of the particle from a fixed point O on the line and is always directed towards O. And we saw that this definition implied that we had x double dot must equal k times x, but the fact that the acceleration has to be directed towards O forced us into having k being a negative constant, and we said that it was usual to write k as being minus omega squared. So we've got our definition. Our mathematical definition of simple harmonic motion is an object that is moving in such a way that it satisfies the differential equation x double dot equals minus omega squared x, or equivalently x double dot plus omega squared x equals 0. Now we can use some of the techniques from Module 4 of the Further Maths specification to deduce many of the consequences of this differential equation. So the equation x double dot or d2x dt squared plus omega squared x equals 0 has an auxiliary equation which is k squared plus omega squared equals 0, which tells me that k must be 0 plus or minus omega I, which in turn tells me that the general solution of the equation is x equals p cos omega t plus q sin omega t, and differentiation of this tells me that the velocity, or dx by dt, is minus omega p sin omega t plus omega q cos omega t. Now, using the R alpha method, the expression p cos omega t plus q sin omega t can be written either in the form a cos omega t plus epsilon, or in the form x equals a sin omega t plus a different constant angle, which we'll call epsilon dash. And all of these equations represent an oscillation of amplitude A and period t, where t is equal to 2 pi over omega. Now, two or three special cases of this which are worth noticing. First of all, if we know that when x equals a, v is equal to 0, when t equals 0, then that means I must have the solution x equals a times by cos omega t. If on the other hand I have x equals 0 and v is positive when t equals 0, then I must have a solution of the form x equals a sin omega t, where a is the amplitude of the motion. And if x equals 0 and v is less than 0 when t equals 0, then the solution must be x equals minus a sin omega t, where again a is the amplitude of the motion. If we take the general solution as being x equals a cos omega t plus epsilon, which is one of the several forms we had for the general solution, then v is dx by dt, and the chain rule tells me the derivative of x is simply minus omega a sine omega t plus epsilon. So v squared is omega squared a squared times by sine squared omega t plus epsilon. But we know that sine squared is just 1 minus cos squared, so we can write v squared as being omega squared a squared times by 1 minus cos squared omega t plus epsilon. Multiplying out the a squared, or multiplying the a squared through the bracket, gives me v squared is omega squared times by a squared minus a squared cos squared omega t plus epsilon. But a squared cos squared omega t plus epsilon is just x squared. So what we've got is v squared is omega squared times by a squared minus x squared. So we have our equations of simple harmonic motion. We've first of all got the basic definition, x double dot equals minus omega squared x. The point O must be the equilibrium position for the particle, because the point that you're measuring away, the displacement away from, is a point where there is zero acceleration, and the point where there is zero acceleration is exactly the equilibrium point position. The general solution of the differential equation can be written in the form px equals p cos omega t plus q sin omega t, or a cos omega t plus epsilon, or a sin omega t plus epsilon dash, where p, q and a are constants, and a is the amplitude of the oscillation, and the period of the oscillation is t, where t equals 2 pi over omega. And then we had the three special cases, that if x equals a when v equals 0, when t equals 0, then we've got x equals a cos omega t. If x is 0 and v is bigger than 0 when t equals 0, then we've got x equals a sin omega t. And if x equals 0, v is less than 0 when t equals 0, then we've got x equals minus a sin omega t. And then finally, we showed that the speed of the particle when its displacement is x is given by v squared equals omega squared times by a squared minus x squared. Now, before we go on and look at examples of this, let's just make one or two important observations of these equations. First of all, simple harmonic motion means that a particle is going to be oscillating between x equals plus a and x equals minus a with a period of 2 pi over omega. Secondly, that the maximum speed is omega times a, and that this occurs when x equals 0. And that's a direct result of the equation v squared equals omega squared times a squared minus x squared. The maximum magnitude of the acceleration is omega squared a, and this occurs when x is plus or minus a. And that is due to the fact that we know the acceleration is simply minus omega squared times by the displacement x. So the maximum size of the acceleration is just going to be omega squared times by the maximum size of the displacement, which is a. And when x equals 0, the acceleration is 0, which means that x equals 0 must be the equilibrium position for the system. And in subsequent videos we will see that this is crucial at the first thing when we're considering the motion of a system. If we wish to show that it is going to be SHM, we must start measuring the displacement away from the equilibrium position. So moving on to some examples of using these equations of simple harmonic motion. Our first example, we're told we've got a particle describing linear simple harmonic motion of amplitude 2 meters, and its speed is 1.4 meters per second when the particle is 0.8 meters from its equilibrium position. We've got to find the period and the maximum speed of the particle. In this case, we're going to be using the equation v squared equals omega squared times a squared minus x squared, because we've been told the value of the amplitude, we've been told the speed, and we've been told a corresponding displacement, and the equation v squared equals omega squared times a squared minus x squared will enable me to work out what the value of omega is. So substituting in, we've got 1.4 squared is omega squared times by 2 squared minus 0.8 squared. In other words, 1.96 is 3.36 times omega squared, which gives me omega squared equals 7/12. So we've got omega is the square root of 7/12, and that means that the period, which is 2 pi over omega, is 2 pi divided by the square root of 7/12, which is the same thing as 2 pi times the square root of 12/7. The maximum speed of the particle is omega times a, and omega times a is simply going to be the square root of 7/12 times by the amplitude, which is 2. So we've got approximately 1.53 meters per second for the maximum speed. For our second example, we've got a particle moving along a straight line in such a way that at time t its position is x meters from a fixed point O on the line, where x double dot is equal to minus 16x, when t equals 0, x is 0.5 and dx by dt is minus 4.8. We've got to find the amplitude of the motion and the position and velocity of the particle when t equals pi by 6. The equation x double dot equals minus 16x tells me that I have got simple harmonic motion with omega squared equals 16, in other words, with omega equals 4. Now, when t equals 0, I've got x equals 0.5, and I've got v equals minus 4.8, and I've also just found out that omega equals 4. So the equation v squared equals omega squared times a squared minus x squared gives me 4.8 squared, which is 23.04, equals omega squared, which is 16, times by a squared minus 0.5 squared. In other words, I've got 1.44 is a squared minus 0.5 squared. So a squared is 1.69, so the amplitude of the motion must be 1.3 meters. Now we know that if I've got x double dot equals minus 16x, then the general solution of that equation is x equals p cos 4t plus q sin 4t. And the velocity expression obtained by differentiating is x dot equals minus 4p sin 4t plus 4q cos 4t. Now if I use the initial conditions, I can find the values of p and q. So when t equals 0, x is 0.5, gives me 0.5 equals p cos 0 plus q sin 0. Cos 0 is 1, sin 0 is 0, so that's giving me p must be 0.5. But I also know that when t equals 0, the velocity is minus 4.8. So I've got minus 4.8 must equal minus 4p sine naught plus 4q cos naught. And that gives me q must be minus 1.2. So the solution of the equation is x is 0.5 cos 4t minus 1.2 sine 4t. And x dot, by differentiation, is minus 2 sine 4t minus 4.8 cos 4t. So if we substitute in t equals pi by 6, that's going to first of all give me x is minus 1.289, and then secondly it's going to give me the velocity x dot is 0.668. For our third example, we've got a particle moving along the x-axis. At time t seconds, its displacement from the origin is given by x equals 12 cos a third pi t. We've got to prove that p is moving with simple harmonic motion. We've got to find the period and amplitude of the motion. We've got to find the maximum speed of p, and we've got to find the time taken by p to travel directly from the point 60 to the point minus 6 root 3 minus 6 root 3 0. Now, to show that something is moving with simple harmonic motion, we've got to show that the equation of motion takes the form x double dot equals minus omega squared x. So if I've got x equals 12 cos a third pi t, then x dot is going to be minus 4 pi times sine of a third pi t, and x double dot is going to be minus 4 over 3 pi squared cos a third pi t. And that is precisely the same thing as minus pi squared over 9 times by 12 cos a third pi t. In other words, we've got x double dot is minus pi squared over 9 times x. So we have the equation of motion is of the form x double dot equals minus omega squared x. So the motion is simple harmonic motion with omega equals pi by 3. The period, therefore, is 2 pi over omega, which is 2 pi divided by pi by 3, which is 6 seconds. The amplitude of the motion is 12, because we've got the solution. The equation of the motion was x equals 12 cos a third pi t, which means that x is varying between 12 and minus 12. So the amplitude of the motion is 12. The maximum displacement away from the equilibrium position is 12. The maximum speed we know is given by omega times a, so that is pi by 3 times by 12, which is 4 pi meters per second. So that just leaves part D to do now. We want to find the time taken by p to travel directly from the point 60 to the point minus 6 root 3 0. Now we know that at t equals 0, the particle is at x equals 12. We can fairly easily, and we know that when t equals t1, let's say, the particle reaches the point A for the first time, and that will be the first positive solution of the equation 6 equals 12 cos a third pi t. So that's the first positive solution of cos a third pi t equals a half. And that will happen when a third pi t is actually equal to a third pi. so when t1 equals 1. So it takes 1 second for the particle to move from the extreme position of x equals 12 to the point A. The particle is going to reach B when 12 cos a third pi t is equal to minus 6 root 3. In other words, when cos of a third pi t is minus root 3 upon 2. And that is when 1/3 pi t is 5/6 pi. In other words, when we've got t equals 2.5 seconds. So it reaches A for the first time after 1 second. It reaches B for the first time after 2.5 seconds. So the time taken to travel from A to B is 5/2, take away 1, which is 1.5 seconds. So that concludes our video looking at some of the conclusions that we can draw from the simple harmonic equation. In the next video we will look at some examples of simple harmonic motion.